I'm getting our YouTube live stream set up. So if you'll give me just a moment to do that, then we'll get started. Okay. That means we're set up. And let's see. Get all my notes and everything set up as well. All right. Well, Happy New Year, everyone. Welcome to this first seminar in 2023. We're really happy to have everyone join us. My name's Jody Peters. I'm the community manager for the Ecological Forecasting Initiative, which we also call EFI. I want to acknowledge that I'm joining you from the traditional and current homelands of the Pokagon Potawatomi in northern Indiana in the U.S. And today we're hosting Elaine Zur and Elena Aino, and they will be presenting about zero inflated models. So the Ecological Forecasting Initiative has been co-hosting these seminars with the Ecological Society of America's Statistical Ecology section, and we have Dennis Valle and Vianney Lejos Barajas, two co-chairs of the section with us today, and we're really excited to co-host the second round of the seminar series. So before we get started, I just want to point you to the GitHub repo link on this screen. If you want to follow along with the code and presentation today, you can get that from the repo, and we'll put the link in the Zoom chat as well. So for today, I'm going to give a brief overview about the Ecological Forecasting Initiative and the logistics for today's talk, and then I'll turn it over to Dennis, who will introduce Ellen and Elena. So the Ecological Forecasting Initiative is a grassroots consortium of individuals who are building and supporting an interdisciplinary community of practice around iterative, near-term ecological forecasts. And we all know the benefits of being able to have weather forecasts and how they help us to plan for upcoming good weather or bad weather. And just like weather forecasts help us to make plans, ecological forecasts are also critical for making plans and making management decisions, particularly in response to changing climate. So this figure shows the iterative learning loop of ecological forecasts, and we can start with real-time environmental data, put that into models, and make computations, make predictions, and use those predictions to make better decisions for society. And I wanted to show just a couple examples of types of ecological forecasts. So there's forecasts for animal and plant populations. There's forecasts for different processes in terrestrial, freshwater, and marine systems. If you can collect data for it, put it into models, you can make a forecast for it. And we want to invite anyone that's interested in forecasting to get involved with the Ecological Forecasting Initiative. Our activities are open to anyone with interests in ecological forecasting. And we've got community members who range in what they are doing in their interests. So we have people who are creating forecasts, people who use forecasts to make decisions, and people who are just starting to learn about what forecasting is. And an easy way to get involved is through our newsletters. So you can sign up for our newsletters on our main ecoforecast.org webpage. We send these out every 4 to 8 weeks, and they provide high-level announcements for what's going on in the community. We also have a number of working groups. So if you want to get a little bit more involved, working groups and chapters are a great way to do that. Our working groups meet monthly and are working on providing and creating open resources, writing manuscripts, and generally just providing support to each other. We have a really active student association where it's led by students who are supporting other students. So if you are a student or know of students, definitely reach out to us and we can get you in touch with that group. And we've got chapters in Canada, Oceania, and Europe. We also have materials that are on YouTube, on GitHub, and we have an active Slack channel. And if you'd like to be part of the Slack group, reach out to us at info@ecoforecast.org. And we can get you connected to that. The other thing that we have going on is our Neon Forecasting Challenge. And so We're working with the National Ecological Observatory Network, or NEON, to provide data for teams to create forecasts for these 5 different themes. And we provide the NEON and the meteorological data, and the community provides the forecasts, and these go onto a dashboard so people and teams can see how well their forecast did compared to the observed data that gets collected. We provide an example workflow and a number of functions and FAQs to help people get started. And this challenge has been used in a number of undergrad and graduate courses. So if it was something of interest to anyone, again, reach out to us. The last thing I want to mention about what FE is doing is that this summer we're hosting an unconference in Boulder, Colorado at NEON's headquarters, and our goal is to bring people together to work on forecasting. Because it's an unconference, the meeting is going to be driven by what participants want to work on. We have funds to support travel within the US. We are limited to by space to only having 50 participants. So we have an application process, and we're using that to balance diversity and demographics, industry, career stage, and interests. And we've got how you can apply here, the link to apply. It's also on our website as well. And these applications are going to close on February 1. So transitioning to today's seminar, our core values are that we treat others with kindness, respect, and consideration. We empower and create space for one another. We welcome and support a diverse community, and we express gratitude and recognition, and we ask that you follow that today. Because we have people joining on Zoom as well as watching this on the live stream through YouTube, we're going to have people submit questions using Poll Everywhere. We'll use the Zoom chat for logistical support, but if you've got questions that you want to be answered during the Q&A session at the end, submit those to Poll Everywhere. It's really easy to get to Poll Everywhere. All you have to do is open up a new web browser on your phone or computer, type in what we have on the screen here, pollev.com/EFI2023, and we'll put that link in the chat as well. But that will get you the place where you can submit questions, and you can also upvote questions that other people have submitted. We are recording the presentation, so if you have to leave early or if you want to go back to this resource later, we're going to make that available by next Monday. And with that, I'm going to turn it back over to Dennis.
Thank you, Jody. All right, so I just want to take a minute to talk about the Statistical Ecology section. So this is a section within the Ecological Society of America, one of many. Our mission is to facilitate a communication between statistics and ecology and sponsor forums like this, where we can talk about advances in statistical ecology. If this is a mission that resonates with you, please consider joining our section. The current officers are myself, Dennis Valley, Dr. Krishna Pacifici from NC State, and Dr. Vianney Leos Barajas, University of Toronto. So our goal with this statistical methods seminar series is to focus on methods that have already R packages available, because we believe that that would be most useful for the folks. And we still thinking about this being useful for most people. We asked the speakers to share their code and walk through it, describing common pitfalls and stumbling blocks. So if you have suggestions for future modeling topics or presenters, please let us know. Reach out to one of the program officers. We would be particularly interested in including speakers from underrepresented groups that can present on these widely applicable statistical models. So having said that, I would like to go ahead and introduce our speakers for today. We are very glad to be able to have Dr. Alan Zur. He's the director of Highland Statistics, a statistical consultancy company based in the UK. And he's interested in statistical methods like GLMMs and GAMs and zero-inflated spatial temporal correlated data. So Dr. Zur holds a PhD in statistics from the University of Aberdeen and master's in mathematics from the University of Groningen, the Netherlands. And we also have Dr. Elena Yeno. She's a senior marine biologist that has 15 years of experience teaching statistics to biologists and environmental scientists. She holds a PhD in biological scientist from CONICET, Argentina, and Institute for Forestry and Nature Research from the Netherlands, and a master's in biological science from National University of Mar del Plata in Argentina. So both of them work in Highland statistics. They have trained over 7,000 scientists from different fields, and they have jointly written several books, including the very popular books series, Beginner's Guide to Zero Inflated Models, Data Exploration, GAMS, and so on and so forth. So we are very happy and fortunate to have them present today. So without further ado, please, Dr. Ellen and Dr. Elena, please take it away.
Thank you. Thank you for inviting us, and thank you for joining. Good. My name is Elena. That is the lady with the nice headphones on. I am at highstat@highstat.com, and Elena is at bio@highstat.com. Though I don't think you're in Spain right now, are you, Elena?
No, I've been traveling from North to South America.
Well, I'm in Scotland. Today is zero inflated GLM and GLMMs. So who are we? Very briefly, we started writing a couple of books for Springer in 2006, 2007. They became a little bit too popular, or Springer made too much money out of that. So we decided to write our own book series as self-publishing authors. And that was, yeah, it's a nice experience. That's because you guys keep on asking questions and we don't know the answer. So we look it up and we write some text around it, and voila, you have a new book. The one we're going to talk about today, or a part of that, is zero inflation. Then before COVID, we used to do 20 courses, 25 courses per year in very nice places. Nowadays, that is all online, but I think that is equally nice, especially because I got two little kiddies running around. But then, yeah, I think it's time to do on-site things again. We try to avoid doing statistical consultancy, already busy enough. You're a biologist, Elena. You're the nice one. I'm a statistician. I try to be nice. What else I want to say? Yeah, what are we going to do today? Outline. First, going to talk about a little bit of a revision of Poisson negative binomial distributions. Then you're going to do that, Elena.
Yeah, that's okay.
GLM. And then I will take it over with zero inflated models. Yes, this is for count data, but where possible, I will also try to give you some hints, some suggestions what you can do for continuous zero inflated data. And then we're going to do a detailed example using some R codes, using a owl begging behavior data set. And if you want to dive deeper in this stuff, then it's either that one. Now, there are always people among you who are quite unfortunate that they have zero inflation, they got spatial correlation, they've got temporal correlation. Yeah, you can combine it all. That's all possible. But before you know, you're doing very difficult things. Okay, let me close this. You do have the PDF files of this, but you can also watch. So let me then open the second presentation. So this is you, Elena?
Yes, that's correct, Alan. And well, again, thanks everybody for joining us. Again, thanks Jordi and Dennis for doing all the work for us. And now it's time to start with this talk. And as Alan said, well, we're going to deal a little bit with zero inflated models. But before you dig into SIP and SAPS models, you need to be familiar with certain type of distributions that will allow you to jump into these zero inflated models. So that's the reason why we always try to work step by step. And whenever we teach these topics, we start doing an introduction about the or describe the most common distributions that we're going to use for later on being able to use in a SIP context. So in this case, I would like to do a revision of Poisson. We're going to start with count data, discrete data. So therefore, we're going to start with a revision of Poisson distribution. And then we're going to discuss negative binomial and generalized Poisson, and finally, Bernoulli distribution. As you will see later on, Elaine will explain you that a SIP model will be comprised of a count part and a present absence part. And therefore, you need to be familiar with both legs, because later on, we're going to combine Poisson with Bernoulli or negative binomial with Bernoulli, etc., etc. So that's the reason why we need to be familiar with both legs before we start doing more fancy things. Now, we incorporated also these GB distributions because they're also available in R, that you can implement that, and it's also very handy when you have problems, not only when you have over dispersion, but also when you have under dispersion. Anyway, if you open a book on general GLM knowledge, you will see that everybody will describe these three main steps. So you first need to deal with the distribution. So you collect your data, you have your Y data, number of fish, number of birds, whatever. And you need to allocate the distribution to your response. Of course, you're going to collect information such as covariates or explanatory variables, and that will be part of what we call the predictor function. And later on, we need to make a link between the expected value of the distribution and the predictor function. So that's the reason why in this presentation, we're going to deal a little bit with the first step, meaning the distribution, and later on, we're going to work towards the GLM models and later on SIP models. So you're going to see that we're going to have finally an application, the OWL data Alan was talking about, and we're going to use the GLM TMB package that is quite handy to be able to fit these models. Okay, so nowadays there was a time that we were struggling a little bit in teaching SIP models because we're not having enough. Well, software was not completely work out, and thanks to GLM TMB, that package is really fantastic and is gaining popularity, and therefore it's easier to implement these type of models using frequentist techniques. But of course, you can rely on Bayesian techniques as well. Now, a very important piece of advice: we never start applying a zero inflated models. We always start simple as first we try a simple ordinary GLM Poisson, and our strategy is to build up the models accordingly. We always learn from submodels. So the idea is to start simple, fit a model, apply model validation, learn from the model validation pictures, and then you can find solutions accordingly. Okay, so this is how we're going to play in this case, this game, and how we're going to analyze the final data set. Okay, so and the other thing is people think that if you have lots of zeros, you have to jump immediately into zero inflation, but be careful about that because you may have covariates that can explain the excessive number of zeros, and you can easily implement a GLM Poisson or negative binomial, and then you say job done, and I don't need to dig into all these new distributions. So let's build up everything step by step. Poisson. So when we start teaching in simple courses, Poisson distribution, well, I would like to introduce an example. So suppose that you want to go to an area. In this case, we go to Canada, we have cliffs, and then we have puffins. And suppose you want to count the number of nests per plot. Okay, so we are going to have counts. And our starting point, of course, is going to be a Poisson density function. Okay, so suppose, and then in the next slide, we have, suppose that based on experience, because you have done this, or these people have done this for a while, suppose that we have that in a 3x3 meter plot, we count an average of 5 nests every time we go there. Okay, this is based on past experience. So we don't expect to observe exactly 5 nests, but maybe we're going to count 0, 1, 3, 4, etc., etc. So by using a statistical distribution, we can answer questions as follows. So what is the probability that I'm going to go back to the field, and we're going to observe 0, 1, 5, 10 nests? So given the fact that the mean is 5, again, I can quantify these probabilities, and we're going to use a statistical distribution. So in the next slide, I have an equation, I have a formula there. So I'm pretty sure you came across with this expression that you see in line 3.1, and it says probability of y equal y, given the mean is equal to mu to the power y times e to the power minus mu divided by y factorial. Well, y factorial is, we talk about high school mathematics. There you have how much it is, 5 factorial. By definition, 0 factorial is 1. 1 factorial is 1. And then if you have the mean, and then, so because y is the number of puffin nests, mean is, mu is the mean, and with all that information, I can now stick it in a number, and I can calculate the probability of, for instance, going back tomorrow to the field. Given the fact that the mean is 5, I can calculate the probability of finding 0 nest, 0.06, 1, 5, 10, etc., etc. What you do with all these numbers is very easy if I can plot those probabilities. So I have a sketch 3 different scenarios. Those are 3 different Poisson distributions for a mean equal 5, what is the example of the puffins. Maybe we have a different scenario where the mean is 10, or even the mean is 15, 100, whatever. What you see, if you go from the left-hand side to the right-hand side, is that as long as you increase the mean, you increase the variation. And this is the characteristic of this distribution. It has only one parameter. The mean is the variance. So we assume that the number of nests, the variable nest, will follow a Poisson distribution, and in which the mean and the variance is given by that expression. So the expected value of the nest is equal the variance equal mu. So only one parameter. And I goes, in this case, is a very small data set. We have only 38 observations. So I goes from 1 to 38. Okay, this is just a quick overview to refresh your memory and what a Poisson distribution, how it looks like. Then a good competitor, and probably the one that in most of the cases the ecologists will go through, is the negative binomial. Again, so as we said before, for the majority of the ecological data sets, you have the situation that the mean variance relationship imposed by the Poisson distribution will not hold. So Poisson is not a very friendly, just to mention like this, it's not a very friendly distribution, something that you're going to use all the time for analyzing ecological data. So there's a reason why in most of the cases when you start trying a GLM Poisson distribution of data, you will encounter problems. And if you encounter problems, you will see at the end of the day that your parameters may be biased and all your conclusions are going to be wrong. So if the variance is larger than the mean, then we can rely on a second option, which is called the negative binomial. Now, as you can see, the formula you have in equation 3.3, we have a new component. It says expected value is the mu, is equal to the mean. The variance is equal to the mean plus mean to the power 2 divided by theta. So it's a new parameter. Now we have the mean and the theta. And the theta, depending on the value of the theta, for instance, if theta is very large compared to mu to the power 2, the second component in that equation will be close to 0. And if that happens, then you go back to the situation in which the variance mean is the variance is equal mu. So then you go back to the Poisson. So there I have the have a sketch of that scenario. So depending on the value of the theta, you may encounter different. You may have different options. And we illustrated the situation here because what we did here, we have 3 columns. So we have 9 different pictures, 9 different distributions. And we have by column, we have some different mean values, 5, 10, and 15. And by row, we change the value of theta. So if you look at the bottom, theta is very large. That was the scenario was sketching. If theta is very large compared to mu to the power 2, then you go back to Poisson. So this is pretty much like a Poisson distribution. Then theta is 1. You see, then you get a different distribution, different shapes. And if you look at the top, then you have the scenario where theta is very small. What you see here is quite characteristic, a large spike at 0. So when we look at these pictures, so it doesn't come to surprise that if you were to have excessive number of zeros, maybe the negative binomial can cope with this scenario. Now, as you can see, let's concentrate on the one in the middle, Alain. Maybe you can help me highlighting the at the bottom. So if you look at the scenario where the mean is 10 and theta is 1000, you can have, we can see here, we can have data on the right-hand side of 10, because 10 is the mean. But you can also have data on the left-hand side, okay? And the data are sort of symmetric around both sides. But if we go a little bit further up, and if we select that picture that Alain, the one that says mu equal 10 and theta is equal 1, then we have lots of values lower than 10 and a few big ones, okay? And it becomes even more extreme if you go to the upper picture where it says mean is 10 and theta is 0, 1. There you have that maybe only a very few, you have only a very few large ones, and you have lots of values on the left-hand side, okay? So what we can conclude, and this is the interesting aspect of this distribution, is that if you were to have observed data that are highly skewed at certain covariate values, the negative binomial is a very good option. And we also need to consider that if you were to sketch the fitted values of the model, it does not necessarily mean that you're going to have, well, you're going to have an exponential relationship, of course, and it does not necessarily mean you're going to have equal number of values the above and below that line. That is what happens when you fit a linear regression model, but that is not necessarily the case because this distribution may not be symmetric. Okay, then we have a good competitor is this generalized Poisson distribution, a GP. This is perhaps a distribution that not everybody will be familiar with. And as I said before, it's a very good competitor for negative binomial because you can target situations in which you have models that are going to be over dispersed, but you can also target situations in which you're going to have models that are going to be under dispersed. So for years, we've been struggling in fitting GP models. Now with a GLM TMB, it's very easy to implement this distribution. And for those, for instance, that it's not very likely that you're going to find situations where you're going to encounter under dispersion. The most likely scenario in ecology is over dispersion. But for those that, for instance, ornithologists that work with data sets such as clutch size data, well, those models, they tend to be, when you count the number of eggs, those type of, when you implement those models, they tend to be under dispersed. So now, welcome back, we can use a GP distribution. And of course, there are different ways, depending on which book you're going to rely on. There are different ways of expressing the mean and the variance of a variable that will follow a GP distribution. And here you have expected values equal mu. The variance is given by that expression. Depending on the package, we simplify the whole thing by saying mu times theta or phi, whatever you want to call. And depending on the scenario, depending on the value of the theta, you may conversion to Poisson. Maybe the next one, Alain, is easier. Maybe if theta is equal, if that one is equal 1, then we have the scenario that will obtain Poisson. If that phi or theta is larger than 1, we assume over dispersion, and if it is lower than that, we assume under dispersion. So that's the reason why we're saying that this one can cope with different type of scenarios. And if you don't have massive over dispersion, maybe the GP can perform even better than the negative binomial. So you have different options. And here I wanted to sketch some of the scenarios with GB density functions we're using the DGEM package. Unfortunately, this DGEM +1 cannot allow us to visualize the under dispersion situation. But what I did, again, I fitted three different scenarios with the mean goes from 5, 10, 15, and different theta values of pi values of 1, 2, and 5. So the one that is at the top is pretty much the scenario of the Poisson distribution. And if phi is 2 or 3, as you can see, we can map the curves are getting wider and wider. So we have this scenario of over dispersion, and if you have a small amount of over dispersion, maybe this is a very good competitor, as I said before, instead of using negative binomial. Finally, we have to deal with the second leg. So a SIP will be combined. It will be a combination of Poisson negative binomial GB plus Bernoulli. So that's the reason why we also have to refresh your memory of what you do when you have to analyze present absence. So you may have present absence data only, and you have to rely on Bernoulli distribution. So say that you're not interested in the counts themselves, in the quantitative aspect of the data, you're interested in the qualitative aspect of the data, you convert everything into present absence, yes, no, and then we know for sure that we can use a Bernoulli distribution that can be expressed by that equation that you see there, 3.5. So we say that expected values of nest is pi. Pi takes the same role as mu, the probability of finding nest, and the variance is given by that expression. Okay, so this is a quick overview of the essential distributions that are going to use for simple zero inflated models. Now, we were talking about 3 different steps, the idea of having the response. So now we define, so you collect data, and the first thing you have to do is define, depending on the nature of your response variable, you need to find a distribution that can later on allow you to run the corresponding model. But now we have to work towards a GLM model, starting with a Poisson GLM. And we're going to use this puffing data. Okay, this is a real data set from a long time ago in Canada. So they were looking at factors that were explaining breeding success in these animals, and they accounted for 4 different covariates. Just for simplicity, we're going to use only one, the last one, distance from the cliff edge, for 2 different reasons. From the pedagogical point of view, it's easier to explain things with only one covariate, but at the same time, we have only 35 parameters, 35 observations. And there is rule of thumb that you need to have at least 20, 25 observations per parameter. So I don't want to overcomplicate things. So predictor function, we have to specify the covariate part of the model. We call this eta, so that symbol there is eta, the Greek letter eta equal intercept plus beta times distance. So this is my, as I said before, my predictor function. I have the y data predictor function, and now we need to specify the relationship between the mean of the distribution, mu, and the predictor function eta. And here is where you have to think what are the options that you have available for you. Default settings are going to be log-link function, but you can also use identity link. And I think in the next slide we have we say identity link will be mu equal eta. Problem is that if you deal with counts, with discrete data, this option is valid in those scenarios where you're not going to expect negative fitted value. So most likely a scenario, default settings, use a log-link function, and that will ensure, thanks to this construction, mu equal e to the power intercept plus beta times covariate, that construction will ensure that your expected values are going to be strictly positive. Okay, so because you don't want to make predictions of having minus 20 number of nests. Okay, so working towards a GLM, and that is the first 3 lines. This is what I will write down in a paper. We always encourage people to write down these equations in a paper, because then as a reader, you know what you're doing. We say that nest I, the y data, is Poisson distributed with parameter mu. Expected value is equal mu, equal the variance. Log mu, which is the same as me saying mu equal e to the power. intercept plus beta times distance, beta times covariance. Now, getting a little bit of working knowledge, we can estimate the parameters of this model using the GLM function, plain GLM, and you use that construction that we saw there. Okay, so what is the first thing you fit your first GLM Poisson? What is the first thing you have to rely on? So you have to verify that the mean variance relationship will hold. So we need to account or calculate the so-called dispersion statistics. So that is going to be a formula, a ratio. If that value is 1, then you're okay. If it is larger than 1, we suspect over dispersion. Lower than 1, we suspect under dispersion. So what are the components of that formula? Well, we need to account to calculate the dispersion statistic. We need to calculate the Pearson residuals, observed data minus fitted data divided by the square root of the variance. Once I have the Pearson residuals, once I have the sample size, once I have the number of parameters, the formula itself will calculate the sum of the square Pearson residuals divided by sample size minus the number of parameters. In this part, for this particular data set, the value is 1.97. So it is definitely larger than 1. One of the, every time we teach this type of models, people are always asking the same type of questions. How much larger than 1 do we have to, or in which scenario do we have to pay attention if it's not exactly 1? Because you may get scenarios where the value is 1.2, 1.5, 1.6. At which point are you going to make corrections? At which point you're going to think about doing something else? Well, actually, out of the blue, to be honest, we wouldn't be able to answer that question. The right question would be, the right answer to that question would be, I don't know. Because it depends on the sample size, it depends on the number of covariates, the type of covariates, so it depends on the model. So what we can see, or the way we can answer the question, is as follows. What we can do is do a simulation study. So the concept is very simple. So you have a data set, okay, like the buffing data. Then you have a model, you apply your GLM model as we specify in the previous slide. From the model, you can simulate, let's say, 1,000, or maybe for a paper, 10,000 set of new number of nests. And for each simulated data set, you're going to calculate the dispersion statistics. And with those dispersion statistics values, you can make a histogram of that. And hopefully those 1,000 or 10,000 dispersion statistic values that you get from your simulations are going to be comparable to the one that you found in your original model. So as you can see here, I have plotted, we did a simulation with 1,000. So we have 1,000 data set, and we calculated 1,000 times new dispersion statistic values. But you don't get exactly, all the values are not going to be exactly 1. So the majority will be around 1, but you can get values such as 0.5, 0.6, 0.8, even 1.5. And probably in only very few occasions, you get a value that is larger than 2. But that value is going to be labeled as rather extreme. So the value that we found, that was 1.97, is definitely very, very extreme. So we can conclude that we see overdispersion. But again, this is a data-specific picture. Maybe if you increase the number of observations, so if you came up with a different data set, like having 100 and 1,000 observations, then those histograms perhaps are going to be pulled towards 1. So the range you will tolerate probably is going to be smaller. So that's the reason why it depends on the model fit. It depends on the sample size. And as I said before, this is a data-specific question, meaning that if you obtain a dispersion statistic of 1.6, maybe it will comply with the Poisson distribution in your scenario, but may not comply in my scenario, okay? So that's the reason why we encourage people to do this simulation study. Of course, you're not going to probably spend time doing all these simulations if a priori you find a value of a dispersion statistic value that is 20, 50. So there is no point of doing this type of simulations because you know a priori that your model is going to be over dispersed. Anyway, in this case, we conclude that we have over dispersion, and the question at this point that you have to answer yourself is, why do we have? So now you have to go deeper in trying to understand why you have over dispersion, okay? So you're not going to jump immediately into a different distribution without knowing which component is causing or what is causing over dispersion. So at this point, you have to do a detailed model validation, and we have to check for nonlinear patterns, dependency, spatial dependency, temporal dependency, et cetera, et cetera. And even if the dispersion statistic of a classical GLM Poisson will indicate that there is no over-dispersion, you still need to apply a detailed model validation before you present your final result. And in this slide, we have all the steps. We summarize all the steps that we always do when we teach. We say, well, okay, model validation is something that you have to pay attention, and you have to extract the residuals, plot the residuals versus fitted values, plot the residuals versus each covariate in the model, each covariate not in the model, because maybe it's a GLM Poisson, but you plot the residuals against a covariate that you didn't include, and you see a beautiful nonlinear patterns, and then you have to go into GAMs, et cetera, et cetera. So you have to put emphasis on covariates in the model and covariates not in the model. Plot residuals versus XY positions, so to deal with later on with the spatial correlation, temporal aspect, and check also for zero inflation problems. So thanks to all these simulations that I have already done, maybe what you can do at this point, well, first I have these pictures, residuals versus fitted values. Within the majority of that gradient, I don't see a cone-shaped pattern indicating massive dispersion. Those points that you see there, those are the zeros. So you don't want to have those bands dominating your pictures, because that may be an indication for zero inflation, so something that we have to deal later on. Then I plot the residuals versus distance, which is the covariate that I was picking up for this analysis, and we see clear indication for nonlinearity. Then Pearson residuals versus grass, that is okay. And then observe versus fitted values, you pretty much, if you have a good fit, you would like to have, perhaps depending on the scenario, points that are going to lie within that line. Zero inflation problems. Okay, I'm using again my my simulation results. And what I can do, I can calculate, what else can I do with those 1,000 simulated data sets? Well, I can calculate the number of zeros in each of the simulated data sets, and I can compare with the number of zeros that I obtain in my original data set. So that big dot in black, it's indicating that in the original data set, we have 13 zeros. And what we have in that frequency plot, we see how often we find 3 zeros in a data set, 1, 5, 7, etc. But for sure, if we simulate it if you simulate data from the model, and if we assume a Poisson distribution, the simulated data cannot cope with 13 zeros, 20, whatever. So it's an indication that we have zero inflation. So we conclude that we have over dispersion, and we detected 2 main problems. The model cannot cope with excessive number of zeros based on those simulations pictures. And there is also an indication of a nonlinear pattern with the covariate distance to the edge of the cliff. So 2 different problems that we have to address. Okay, so and now what do you do? Well, before you start thinking of moving on, before you start thinking of changing the distribution, it is highly recommended that you sketch the fitted values. We always put emphasis in sketching the fitted values, even if this model, you know, a priori that is not going to work, but I will try to get familiar with the model fit so that I can disentangle the components that later on will allow me to think about how I'm going to improve my final attempt. So what I'm doing here, because it's only one covariate, I'm sketching the fitted value. So number of nests, so the line in the middle, that is the fitted line. I have in gray the 95% confidence intervals around the mean. Those dots are the observed values, okay? And then we have the covariance distance to the cliff. Maybe it's better to look at the second picture, because I can now rely on a three-dimensional picture. And what I have, again, I have my covariate data distance to the cliff. And in the third axis, I have the density curve. So what I'm doing is at every covariate value, at every distance to the edge value, I'm superimposing a Poisson density curve. And I'm superimposing also the raw data. So what you can see, and this is the characteristic of the Poisson, when I have distance values, very low distance value, the range that this distribution is covering is very wide. But as long as you increase the value of distance to the edge, then you see that the curves are getting less wider. And if you look at the last two, there is where you see a cloud of points. Those are the zeros. So I'm not worried about the last one. I'm worried about that one, the one that Alain is highlighting. So it seems to me that those zeros, they don't comply with the Poisson distribution. That's the reason why we're talking about zero issues here, so zero inflation issues here. So apparently, at that specific covariate value, those zeros, they don't comply with the Poisson distribution and can be labeled later on as excessive number of zeros. The other thing I can do a third picture, and this will allow me to, again, sketch the fitted values. So I have the line itself, the fitted line. I have the dots in black are the observed values. And what I did here, I picked 20 distance value, and at every distance values, I'm simulating new number of nests. So using the mean value. So for instance, for the first, the one that Alain is highlighting there, the mean is 17, I think, something like that. So using the RPOS function, I can generate new Y data, and I'm simulating 50 values. So for every specific distance value. And I'm doing the same at the right-hand side. So at every covariate value. And again, if you concentrate, if you put your, if you zoom in where it says distance equal 40, there is where everything I have simulated. So those zeros that you see there, they don't comply with the Poisson distribution. So this is something that we have to definitely, you need to investigate.
Elena, can I just add something?
Yes.
If you were to do this 250, if you were to simulate 250 values, and if you compare the observed data with the simulated ones, and if you were to calculate the fraction of the simulated values smaller than the observed one, you're very close to scaled quantile residuals. And why do I say that? Because in 2 or 3 slides, you will see the phrase DH-ARMA, which is using scaled quantile residuals. But that is what it's actually doing. Simulate and compare simulated data with the observed value and express that as a fraction that is smaller. Now you know what DH-ARMA is doing.
Yeah, okay, thanks, Alain. And the other thing is, when we say, okay, now it's time for a change, now we have to think carefully what we're going to do. The idea of learning from these submodels, because I'm not going to present these results because the parameters, they can be biased. So you won't be able to trust, in this case, it's frequencies, the p-values that come from those numerical outputs. But the thing is, you have to, before you feed alternative models, you also need to think which component of those problems that you are encountering will have the first opportunity to deal with. Because, for instance, do we really have zero inflation? Well, apparently, at one particular distance value, I'm not able to explain those zeros. But the other thing you have to think is when you do your model validation, maybe when you have multiple plots with lots of zeros, especially in a row, that can also be an indication for spatial correlation. Or if you have a temporal aspect in your data, if you have lots of zeros sequential in time, that also can indicate that you have an autocorrelation function. So maybe you can also have nonlinear patterns based on the plots that we've seen when you were looking at residuals versus a covariate effect. So what I'm saying is that you're not going to start building up a model with all the complexity at the time. The idea is to go step by step, and from every model that you're fitting, you disentangle all these components, and that will allow you to know how we're going to build up the next follow-up analysis. Maybe you have to do zero inflation, but maybe you have to go into the corner of GAMS, nonlinear patterns. Maybe you have to go to the corner of spatial correlation. So the alternative distribution, if I have that, if I can see that the range that Poisson is showing us in those three-dimensional pictures, if that is not enough, maybe the alternative is to deal with a different distribution. Maybe you have to rely on the negative binomial. So you have to do a negative binomial GLM or a GP GLM. In that case, again, I refresh your memory of the formulas. The link function is the same, mu equal e to the power, log link for both scenarios. And the only thing is that thanks to the theta will ensure that we're going to make those, we're going to have those curves wider and wider. So it's a matter of implementing these competing models, do a detailed model validations, and learn from these, again, new submodels, and see later on what the follow-up or what the final analysis is going to be. Perhaps in this case, if I remember well, for this specific puffing data, GP model was doing the job. Finally, if you, because Alain is going to do the SIP, so we not only need the Poisson, GP, and negative binomial, we also need the Bernoulli distribution, the GLM Bernoulli. So you have to be familiar with this final leg as well. So in this model formulation, I convert everything in present absence. So the first line of code is doing everything as 0, 1. That's your new response. So it's a vector with zeros and ones. And we say that we'll call nest 0, 1. That Y data is going to follow a Bernoulli distribution with parameter pi, expected values pi, variance is given by that expression. And now we're going to use a different link, a logic link. So pi is equal e to the power intercept plus beta times covariate divided 1 plus e to the power, etc., etc. That link, new link, will ensure, the logic link will ensure that everything that you're going to get as theta will be bounded between zeros and ones, because the probability is always between 0 and 1. And so this is the model I can implement. As you can see, I changed the scenario here. I'm not using distance to the edge. I'm using the percentage of grass. But anyway, that I'm feeding a model with only one covariate. This is a GLM with what is a Bernoulli distribution. From the software point of view, we type it in family binomial, but this is present absence, and this is the numerical output. So you have the estimated parameters to fit your to get your eta component, and later on do e to the power divided 1 plus e to the power. Classical, this is classical logistic regression models. So you will have a sigmoid, kind of sigmoid curves, zeros and ones. So in this case, the larger the grass cover, the higher the probability of finding nest. So we need both components to build up later on a SIP model. So hopefully this was meant to be a short revision of Poisson, negative binomial, GP, and Bernoulli, and the implementation of the corresponding GLMs before you jump into the SIP themselves.
Thank you, Elena.
Okay.
Thank you.
Yeah.
I see a heart floating over the screen. Where's that coming from? Okay. SIPs. The world of zero inflated models. Count data. If we were to do count data and continuous data, it would even be longer than what it's going to be today. But I will try to give you some hints for continuous data. So what can we do with count data with plenty of zeros? And assuming that your covariates are not going to help you to model the zeros. You've got zero inflated Poisson models, we call them ZIPs, and you have zero altered Poisson models, ZAPs. And there was a time we would do both. But I think ZIPs are easier to understand and explain And the other problem with ZAPs, what do you do in a ZAP? You first analyze the data as absence presence using a Bernoulli, and then you dump all the zeros and you model the presence only data. And then in step 3, you combine that. Problem is that if you dump all the zeros and you apply a new model on the data without the zeros, yeah, sometimes you don't have much data left. So the type of models that you then can apply in terms of complexity, modeling dependency, random effects, spatial correlation, etc., is quite often very limited. So that's the reason we're not really a fan of zero-altered Poisson models and their negative binomial cousins. So today is going to be ZIP and the negative binomial version of that, zero inflated negative binomial. And yes, you can also do the GP version of it. So ZIP, ZENB, ZIGP. And I always think that the best way to understand a new model is to simulate some data, because then you can keep it simple. There's not too much noise. We all know what we have. So simulate, and then once we've done this presentation, we can take a real data set and then dive into the real problems. And as Elena said, never start with a zero inflated model. First, try an ordinary GLM, like a Poisson GLM, and then apply it, model validation, and see what is wrong. That is probably the best approach. Don't transform your count data and then apply linear regression. Wharton et al. Give you a nice presentation on that, a nice paper. And on top of that, even if you transform data, you're still going to get a problem that there are a lot of observations with the same value. So it's not going to help you at all. So forget about a square root transformation or a log y plus 1. It doesn't help you. Let's do a conceptual explanation of zero inflated Poisson models. Now, Elena, you did the Bernoulli one, the Bernoulli GLM. And what did you do? You modeled absence presence of puffin nests. Yeah, I keep on talking about puffins, but it's not puffins, it's puffin nests.
The nest. Anyway,
Yeah.
doesn't matter. Yeah.
Anyway,
And I know what you're going to say. I consider 1 as success and 0 as failure.
Yeah. So 1 is presence, 1 is success, and 0 is failure. And then you model pi, the probability of success, as a function of covariance. In this case, grass coverage or something like that. Now, in the ZIP story, we're going to change that. We're going to change the definition of the pi. It's slightly confusing. All what we do, we consider 0 as success. So this is absence. That's going to be success. And that is going to be failure. We'll just flip them around. Just technical thing. And that means that a large pi, large say 0.9, means a high probability of not having any puffin nest in a plot. Now, what did you do, Elena? You modeled you actually had absence presence, and you modeled that as a function of a covariate. You can either plug in covariates, or in this ZIP storyline, maybe you want to keep it simple for the moment and don't plug in any covariates, because it is already difficult enough. And if you're going to add covariates in your Bernoulli part, you're only going to get more dizzy. Now, I will show you in the OWL example how you can actually recognize that you may want to consider plugging in covariates in there. But the easiest thing to start with is covariates in your count part and just a constant in your Bernoulli part. You don't have to, but it makes your life a little bit easier. So then I thought, how can I simulate something? Well, if you simulate, you choose regression parameters. So I chose an intercept of 0.5. And how much is e to the power 0.5 divided by 1 plus e to the power 0.5? That is 0.62. So the probability of absence 0.62. And why did I choose that? Because I wanted to have more zero. I wanted to have an excessive number of zeros. 0.62 is pi. So if you want to memorize that, or memorize the 0.5, I just choose it. Here I'm actually doing it in R. Pi is 0.62. Then what I want to do, I want to simulate zeros and ones. I just pretend to go to the field and sample 1,000 plots. So 1,000 times I'm going to simulate a 0 or a 1. And I can use R binom for that. And if you say size is 1, it means you flip a coin only once. So a binomial becomes a Bernoulli. I just need to fool R binom because R binom thinks that that 1 is success. So if you do 1 minus pi, you just make sure that you're going to get more zeros in this case than ones. So you can see that. So with that random seed, nearly 600 times a 0 and 400 times a 1. Okay, I could simulate that. Now, why would I do that? Let's say we also got counts. Actually, that's what you have. You have counts, numbers of nests per plot. The next thing I want to do is simulate count data with lots of zeros. Now, I'm going to use a Poisson distribution for that, but I need to fool this Poisson distribution in some way that I have excessive number of zeros. Now, how can I do that? Well, look, this part, you've seen that. Logit pi is, was it 0.5? And I'm going to use log mu is an intercept plus covariates. Choose what you want. And nest is Poisson distributed. And here's my little trick. I am doing mu times W, where that W thing is the one I just simulated. So mu times a vector with zeros and ones. Here's your model. Let me choose an intercept of minus 0.1 and a slope of 0.05. And I'm using 1,000, so I've got 1,000 plots, so I need 1,000 distance values. Just choose them nicely. You can either simulate them random from a uniform distribution or just nicely as a sequence. So now I got my mu. How do I get my count data? R plus 1,000 values where the mean is mu times W. Mu times W. Okay. What is the trick here? If you simulate from a Poisson distribution where the mean is 0, then your simulated value is also 0. So wherever you are 0, your simulated value is 0. So all the W's that are 0 will give me a 0 for my count. That's how I simulate count data with a lot of zeros. Let me then combine the data. So I just call that zip data. I got my distance and my number of nests. So this is actually what you would sample in the fields. You don't have that W and you don't have that mu. You don't have the intercept, neither do you have the slope. That is what you want to estimate. Yeah, this is what you measure, distance and nests. Now, if I plot that data, look, this is what I have. And those of you who got zero inflated data may start to recognize things because every time I see zero inflated data, it looks, look, big band of zeros there. And then these are your non-zeros. And a massive spike at 0. Simulated data. Let me just plug in everything together. So I call this fantasy. It's a data frame. I got my plot number. I got my covariate. I got my simulated W, my mu, W times mu, and the nest. So again, distance and nest are real. The rest is just made up to simulate. You don't sample, see, you don't know the W, the mu. You estimate them with a zip model. Okay, let me apply this then. So a zip distribution. in the same way that Elena said nest is Poisson distributed, I can say nest is zip distributed. Now the zip distribution got two parameters, the mu and the pi. And yes, I will show that distribution in a moment. I can again have my vertical bars. Now, if you take a pen and paper and you write out the expression of the mean and the variance, just take for granted that this is what you will get. So if you were to know the mu and the pi, then this is your expected value, and this is your variance. Why do you need the variance? Just in case if you want to calculate Pearson residuals. And what do we do with the mu? You are e to the power an intercept plus beta times distance, and pi, let's keep it simple, an intercept only. What would happen if pi is 0 or close to 0? Then you're going to get a Poisson. If you're gone, you're back to the expressions that Elena showed you. Poisson, the mean is the variance.
So they are nested. Yeah.
Yeah. How can you fit a zero inflated Poisson model? Well, you can either use PSCL, and the syntax is zero inf nest is an intercept. You don't have to write one; you can just omit it. Plus, you covariate vertical line, and this is your Bernoulli part, an intercept only. You want to use GLMM TMB so that in a moment we can add random FX, because that one can't do random FX. So that is the reason we're doing GLMM TMB. This is your count parts. ZI formula is an intercept only. Family is Poisson, negative binomial, GP, etc. Beta, that's all possible. Here's the output. Conditional model, this is your count parts. And you got an intercept, an estimated intercept goes there. You got an estimated slope, very similar to what I simulated or what I chose for my simulation. And I've got an intercept for my Bernoulli part. Yeah, that's all very nice because it's simulated. So what do you do next, Elena? What's the first thing that you do after fitting a
I was checking the dispersion.
You check your dispersion. So I'm following the same red line that Elena was doing, except my distribution is different, but my working steps are identical. So give me your residuals. Yeah, I don't know when I made this presentation, at that time it says, I'm not going to do it for you. I think it is still saying the same thing, GLMM TMB, but there will be a point in time when it will do that for you. Now, I have to do it manually. I need to calculate 1 minus pi times the mu from the count part. So how do you do that? Well, get an X matrix. So this is the point where you really have to actually do all these things yourself. Look what I'm doing here. Got an X matrix. I got my betas. Because it is GLMM TMB, you have to do $ conditional. X times beta e to the power. That is your mu from your count part. How do you get the estimated intercept from the Bernoulli? Just look it up. This is how you find it. $ZI. You got your pi. If you got the pi and you got the mu, look what I do. These are your expected zip values. The variance, Pearson residuals, and then it is take the Pearson residuals, square them, add them all up, divide by n minus p. That is hopefully 1. Yeah, in this case, it is actually very close to 1, but that is because it is simulated data. And you're going to get the same problem if it is for real data, because you're going to get 1.5, 1.6, 2. When is that actually good? When it is not good? Well, I don't know. Why don't you simulate 1,000 data sets? And then for each simulated data set, you calculate the dispersion statistic. Either simulate and hope that that works okay, or you dive into the vegan package and you grab that function, that will simulate zero inflated count data for you. So now you got 1,000 simulated data sets, and for each you calculate, yeah, whatever you want. What about a dispersion statistic? Voila. In this case, it seemed that the dispersion statistic that we found for our model and data complies with those 1,000 simulated ones. You don't have to take the dispersion statistic. You can calculate anything from your simulated data set and compare that to what you want to do with your simulated data. In fact, look who's there, DHRMA. DHRMA is calculating a slightly different dispersion statistic. It's not the one that I showed you before. It's a different one. So don't get confused if you are going to use DHRMA and that the dispersion statistic has a different value. So DHRMA is doing all that simulation for you. And I will show you that in the R code in a moment. And why would you use DHRMA? Well, if you have count data with lots of values that are the same, lots of zeros, lots of ones, lots of twos, lots of threes, fours, fives, then model validation becomes a bit of an art. And in the most extreme case, that would be Bernoulli data. And then you have to use, you better use DHRMA. Other than that, nothing too worrying. Well, I'm bluffing a little bit in here. This is truly zero inflated data, but it is already difficult to do a model validation here. And look at that. This is observed data versus fitted data, and is not on that one-to-one line. So memorize that or remember that, because in a moment I'm going to focus on this. Now, a zero inflated model, they are designed to cope with zero inflation. I haven't seen one single zero inflated model that wasn't able to cope with a zero inflation, which explains why the what was it, Elena? 62% of zeros? I think so. 62% of zeros model can easily cope with that.
Indeed.
Okay. Zero inflated Poisson model visualization. Look who's here. This is your mu from the count parts, mu pos. That straight line there, that's your pi. Remember, pi was constant. And how do I get the mean values of the zip? You do 1 minus pi times that one, and that will give you this. So what I'm showing here is a cloud of non-zero data, yet the fitted values here of the zip are in no man's land. Now that's odd, isn't it? Yeah, well, did we not say that these negative binomial distributions, they're not in the center, they're not necessarily, the mean value is not necessarily in the center of the data. It sits in the middle. Not in the middle, somewhere in the middle. So how does that then work? And going back one, and then people say, yeah, I'm only interested in that one. No, you can't dump the zeros. If you want to make predictions, it's really from that line. These are your zip expected values.
Sorry, Alain, before you move on to interrupt, and it looks as if you have 4 lines. Well, in reality, at the bottom, you have the zeros, okay? Those are
the zeros there too.
Yeah, the zeros are there.
A little bit of jittering. Now, look at this here. Only the black line, the thick black line there, that is the zip average. Here you can see the Poisson. Do you see that? That is Poisson, the count part of the zip. It's not Poisson, it's the count part of the zero inflated distribution. And then you got a spike at 0. A spike at 0, and here you got a Poisson. So it's like the negative binomial. The negative binomial can do something very similar. So a distribution that sits on top of that big black line and that has a spike at 0. But that's all what a zero inflation, a zip distribution is doing. And what would be the zero inflated negative binomial do? A spike at 0, but much wider, a much wider distribution for your count data. What would happen if you do a Poisson GLM here? I can do that. Look, GLM family is Poisson. What's the first thing that you do after a Poisson GLM? Over dispersion. It's over dispersed, so it's not good. Then some people do quasi Poisson, but the problem there is that it will come up with very wide confidence intervals to get the zeros and that data that is far away. Whereas a zip will give much smaller confidence intervals. So a zip is just designed for this type of data, and that quasi-Poisson is not the right thing to do. Now, that is that. Elena, do you mind if we do the story of the true and the false zeros after the OWL presentation, time-wise?
Fair enough. Yeah, fair enough, because we're running out of time. Yeah.
Running out of time, but
I can do that later. Yeah.
Yeah. Okay. Now, without rushing, I don't want to rush. I want to do a real exercise. And then I'm going to have all these graphs that I showed to you on a real data set. Elena, would you be able to tell a story about the owls? Because you're a biologist, you can do it better than me.
Okay. You want me to explain the...
Yeah, explain what it is.
Yeah, very quickly. I mean, we have 27 nests, owl nests, somewhere in Switzerland. And what we have in the nest, those are chicks. And the chicks are making noise because they're begging for food. And in this case, they quantify 30-second intervals of number of noises, number of POs that they do, 15 minutes before the parents arrive to the nest delivering food, and they deliver food. So that's the reason why they standardize all the numbers that were counted in a period of 30 seconds. Those are going to be, so number of calls, count data, discrete data, so that is going to be a response. And we're going to have, as covariate, we're going to have the arrival time. These animals, they feed during the night from 10 o'clock up to 5 o'clock. That is your arrival time. Then we have the sex of the parents, because both parents are feeding the chicks. And we also have a food treatment consisting of, one level is a factor with 2 levels, satiated and deprived. Satiated means that the chicks will rely on 2 different sources of food, and deprived is that they only rely on the food that the parents are going to bring. And that's the reason why we're going to model the number of noises as a function of arrival time, sex of the parents, food treatment, and brood size, which is the number of chicks in a nest. That can. But
then I wanted to keep it simple.
Yeah, that's that's for sure. Yeah, then go ahead. Yeah.
Yeah. Thank you. So owls, load the packages. I don't want to spend too much time on all the ins and outs of the R code. It is well documented, I think. So number of calls is your response. Convert the coordinates from Swiss to data that you can put in ggmap. There's a time element in there as well. Where are we? Switzerland. Near a lake. Yeah, so every dot is a nest. What do we have? Number of calls. So this is the number of calls during the night. 27 nests, 26% of zeros, something like that. Lots of zeros.
26.
Data,
26. Yeah.
Yeah, the data goes from 0 to 30, and the rest looks okay-ish. There is no collinearity. Now, this is an important one. This is your number of calls against arrival time. It is not linear, as you can see. And why would it be linear? Now keep in mind you're doing e to the power relationships, but at the very end of this solution file, I will tell you, repeat everything with a GLMM. The nest effect, 27 nests. It is in fact time series data. What we're going to do, a random effect nest to model the dependency inside a nest. We have 26% of zeros. So how do you start Poisson GLM? It's the same Poisson GLM that Elena talked before, except random effect nest to take into account dependency. You run it. I have only 10 minutes left. You run it. What's the first thing that you do after fitting a Poisson GLMM, Elena?
Check for the dispersion statistics.
Yeah, check for dispersion. Look, there's a function test dispersion that does that for you. It is okay-ish. That's okay-ish. Was this DHRMA, test dispersion? I think it is. Yeah, that is DHRMA.
Yeah.
So just. Can you cope with the zeros? No. Oh, look, it can't cope with the zeros. So this is knock, zero inflated. But before we do that, give me those residuals and plot them against every covariate in the model and check them, in this case versus arrival time. And look, you've got non-linear patterns in here. So you got zero inflation and you got a non-linear arrival time effect. If you want at this point and jump into a GAM, go ahead. Homework, do a complete model validation. I want to show you that 3D graph. So how do I plot the fitted values? Give me 50 values for arrival time for every level of sex parent food treatments and predict. And voila, here are your fitted values. And what is the Poisson distribution doing here? And now it's interesting. So it's a bit of fancy code. So I'm going to pick upon this one, and I am going to superimpose those Poisson density curves on top of it. So for female deprived, ugly code, very ugly code, plot 3D, blah, 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 take for granted. There you are. Oops, come back. So what you see here is a Poisson distribution, and it tells you, I don't like these zeros. It doesn't like it. They don't comply with that distribution, or the distribution doesn't comply with the data. That's probably what I should say. So it's not only that you want to have a non-linear red line, but you also want to have something else for that distribution. Then what is the code doing? The code says, the DR code, it goes on with a negative binomial. Yeah, of course, it's going to get wider. And then it says, let's do a zero inflated distribution. And all what that is doing, it puts a spike at zero. It's exactly that. It's the only thing it does. So a spike at zero. And of course, these things get a little bit smaller because the sum of that distribution has to be 1. But that is the effect of your zero inflated distribution. Elena, what else shall I show of this? I mean, it's pretty well explained. Wrong approach, negative binomial. Look, and binom 2 does that.
Maybe the model fate of the final.
Let me show you the actual zip model.
Exactly.
Values. This is copy paste, copy paste, copy paste. What is the negative binomial distribution doing? Of course, you're going to get the same problem, non-linear patterns. You're going to get wider confidence bands now, but superimpose the negative binomial distribution on there. And they should be wider.
They get
Look, this is a
wider.
negative binomial distribution. Yeah, they do allow for the zeros. Maybe I should have picked upon one of these other ones, because here actually indicates that zero inflation is okay. But if you do a test, it tells you, I don't like the zeros. Yeah, okay, if you don't like the zeros, I will give you a zero inflated distribution. Look who's here, zip. This is the same model that you've seen twice now, except I've added a random effect. How do you do it? As before, ZI formula is an intercept plus your random effect nest. And let me then show you how that works out. Summary M3, you're going to get your estimated intercept like for the was it a puffin, the count parts, the Bernoulli parts, you combine them, etc., etc. Model validation. Of course, this thing now tells you zero inflation, no problem. And it still has nonlinear patterns. So this is definitely a GAM. Fitted values. Let me just show you the 3D picture, because that
that's
is
the one.
probably,
Yeah.
yeah, there you can see it. There's a lot of code. There's only problem here that it is quite requires fancy code. So you got your fitted values. Here, what is the zip distribution doing? Pick one of these. And there we go again, 3D picture. Meow. I say go so. Look, looks very similar to your Poisson, but it has a spike at
Spike.
zero.
And
Then
by
my question, and that is probably the last question I'm going to ask, how would you now know that you could potter around with that pi? Because I'm using pi as a constant in the Bernoulli part. So that thing is constant. How can you allow that, for example, for deprived female, you have a difference in spike compared to here? Because you can see you got more zeros here than there. So maybe at this point, maybe if you want to increase the complexity of the model, allow for a covariate like sex parent or food treatment in the Bernoulli parts, because then you allow for a difference between treatments in the height of that line. Phew, Elena, I think that the best thing is to not go any deeper in this. It does a zero inflated negative binomial, but I guess you get the picture.
You get extensions, yeah.
Yeah, it compares them all, and at the very end, the very end, look who's here, a GAM. Why is it a GAM? Because you really have a nonlinear arrival time.
Arrival time.
And why is that? Parents come with food, chicks make noise, they eat, and what do you do after you eat?
Stay quiet.
You be quiet, you go for a sleep.
And then they go.
After a while, you wake up, you make
They
noise.
get noisy again.
That's what the biology of this is. So the whole story starts over again. Start with a Poisson, GLMM, check for overdispersion, zero inflation, etc.
But as I was making those preliminary comments, we go slowly, step by step, and we learn from every submodel until we get the final one.
And why would you do that? Because a smoother may fight with the zeros, with the zero inflation component. And by the way, you also got spatial correlation here.
Exactly, because those nests, if they're close to one another, they may interact, parents may be competing for food. So there may be correlation between the nests as well. So that's the reason why it may get as complicated as you want, but you need to deal with all these components step by step.
All right, so thank you, Elena and Elaine. I think we have time for a couple of questions. It's almost 1:30. So I'm here at Poll Everywhere. I'm looking at the questions that were voted, or upvoted. So the first question is, how do we choose from zero inflated Poisson or negative binomial when we can see that there's a zero inflation problem?
If a Poisson is over dispersed, and if it can't cope with the zeros, then it's either negative binomial or zero inflated or a zip. How do you choose between them? The negative binomial would most of the time allow for more variation in your count data.
In the counts.
So if there's not only zero inflation, but also large variation in data, then most of the time it's going to be negative binomial. It doesn't happen very often that we end up with a zero inflated negative binomial, because that is a massive cannon to shoot a mosquito, a fly. Yeah, so sometimes you have to gamble a little bit. Is it a zip? Is it a negative binomial? If possible, keep it simple with a zip, because negative binomial, although there are a few papers that actually argue that a negative binomial tends to be better.
Great. The other question is generalized Poisson distribution similar or different from the quasi-Poisson in RGLM?
I don't know RGLM, so I can't answer the question, but I do know that a generalized Poisson is a real distribution. It's a real model, whereas quasi-Poisson, there's no distribution. It's just that you blow up the standard errors.
It's a quick and dirty solution to blow up the standard error.
And then the other thing is in that when you do GLM, yes, you can do quasi-Poisson, but what do you do if you've got spatial correlation and you want to move towards INLA, where you don't have that option? So then you have to go for a GP or a Poisson or for negative binomial. So in all those years that we've done stats, we never done quasi.
And besides, Alain, it can be complicated if you have too many covariates and if you want to enter in the world of doing model selection as well. So that's the reason why we try to stay away from quasi-Poisson distribution.
But maybe other people got different opinions.
And then there's a question here: what can we do with zero inflated proportion data?
Proportion, that is also an interesting one. If your proportion is 0.5, 0.6, 0.7, 0.1, you are in the world of a beta distribution. And a beta distribution, you can also extend that to zero inflated beta, or one inflated beta, or 0 N1 inflated beta. That is all possible. If you're, so that would be the beta route. If your data is 10 fish die out of a batch of 20, then it's binomial.
Binomial, yeah.
So in that case, I would suggest that you go the binomial route. So there's a very fine line. Actually, it's not fine line. It's a quite clear line that says this is beta, that's binomial.
Yeah.
But both of them have extensions towards zero inflated
Definitely, yeah.
examples.
Mm-hmm.
And there are plenty of papers out there that will give you the mean and the variance of a zero inflated beta. And we actually went through all this, did this zero inflated beta stuff in 2014, 2015. We did that with JAX. That was a nightmare to do.
Oh, yeah.
Whereas nowadays you can do that in GLMM TMB. Very, very nice, very fast.
Yeah.
Yeah. And I think related to that, one of the questions that has been upvoted here is, and I think you mentioned briefly about that, of using the alternatives for continuous variables, which also have zero inflation. So you were mentioning the beta regressions with 0 or 1 inflated data, but then what to do with other types of continuous variables that have zero inflation? And the question even asks if the Tweedy distribution is a good choice.
Yep.
You want to answer that, Elena?
Yeah, the Tweedy distribution is a very good option. The alternative is that you you use, in the same way that we use Poisson versus Bernoulli, we can use Bernoulli, and for the continuous part, we can use a gamma distribution. But that is pretty much what is driving the present absence, and once the animals or once the system is there, what is driving the abundance, and then you use the gamma, but gamma has the limitation that is for non-zero data. So it's continuous data, positive, excluding the zero. Okay, so in a combination with a Bernoulli, then you can do a zero-inflated model for continuous data. That is one option. The limitation is that if, depending on the sample size and depending on the number of zeros, when you split up the data into present absence and the presence only, maybe the presence only, we have only a few observations, and then you're not allowed to include too many covariates. And there's where probably Tweety is better. So it depends on this scenario, but both options can be available for analyzing zero-inflated continuous data.
Elena, in our zero inflation course, did we not say your options are Tweety, as you say, and your gamma
Zero.
plus Bernoulli, but the Tweety will, the shape of the Tweety distribution is very similar, although it's continuous, but it's very similar to that zip with a spike at zero. So the Tweety can look very similar. But the Tweety would not allow you to write a story around your zeros. So
Exactly.
if you got plenty of zeros, what is the Tweety doing with that? Yeah, a spike at zero. Whereas the Bernoulli plus gamma, in that approach, which is called a hurdle model approach.
The hurdle model, yeah.
In that approach, because you've got your Bernoulli part, the Bernoulli leg of that model, your zeros can actually tell you a story.
Exactly. So what you can say, you can explain what is driving the present absence, and then what is driving the presence. That is, from that point of view, is probably better if you want to disentangle these two different components. But as I said, there is also a disadvantage. It depends. Sometimes when you split up the data, you have only a very small number of observations in the non-zero data. And that can be an issue as well.
Just apply them both and do it.
Yeah, exactly. That's
do a
what we
hurdle
do.
and see
Yeah,
who's got to tell what.
Yeah. So last question that I think we have time for is if you can use the function check over dispersion in the performance package to check if the Poisson or negative binomial GLMs are over dispersed or not, rather than calculating the Pearson residuals dispersion statistics kind of by hand or through R.
I prefer to do it by hand, because then I know what a package is doing. My first encounter with DHRMA, I got utterly confused because it is actually calculating a different test statistic. So I really went into the source code of DHRMA and try to figure out what exactly the package was doing. And only then I was convinced it was the right thing to do. So yeah, with that respect, I trust DHRMA now. But if you ask me about different packages, I don't know. I can't tell you. I haven't used, well, I did use performance, but I would say double check and look in the source code.
Double check, yeah, probably
double check.
Yeah.
So
for the first time, when we started working with this type of models, we try to, in general, same when we do simulation studies, we try to get a little bit more of control in the code we produce. So check both. Yeah, I would say.
So to be honest, I don't know. I don't know.
All right. So I think for today, that's going to be it. There are many additional questions in poll everywhere, but unfortunately, we won't have time to go over these additional questions. Again, I would like to really thank Dr. Ayeno and Dr. Zur very much for providing this this introduction to zero-inflated models. In particular, I really appreciate that the code is very well documented, and it's going to be a very valuable resource to the community. So with that, thank you all.
Well, thank you for everybody. Thank you everybody attending the talk.